My fellow Americans, there is a clear and imminent threat to our way of life: ISIS. And the answer to this ISIS threat is catapults. That's why I put a bill before Congress called the Affordable Catapult Act. By making these catapults cheaply, the American people can be more prepared for an ISIS attack. This prototype catapult consists of popsicle sticks as the base, frame, and lever arm, a dowel rod stop and a dowel rod pivot arm, various fasteners, a shot glass projectile holder, and rubber bands as tensioners. And last but not least, the flags for 10 added horsepower. Now to General Shathid with the physics.
Okay, this is General Shathid here. Let's take a look at a launch of our catapult. Okay, now after we've watched it full speed, let's flip over to Tracker and do some analysis on it. So at this point here, you can see the catapult is in the locked position, back, ready to launch. This is where all the energy here is potential energy. So at this point, we have no kinetic energy. That's what helps get us to the left side of this equation here. Now, if we go back to Tracker, we go a few frames forward here to 261. This is where the ball is just leaving the cup. So at this point, the rubber bands, if you take this as your baseline for the stretch of the rubber bands, there's no potential energy here. And then you have the ball launching out of the cup, which is completely, all the energy is converted to kinetic. So that is how we get this equation here. Now, considering that the energy is all spring energy, we have 1/2 kx squared as our potential energy equation and 1/2 mv squared as our kinetic energy equation. So in order to solve for k, which would be the spring constant of all the rubber bands on the catapult, we'd use mv squared divided by x squared. So when you run the numbers on that, 0.01 kilograms being the mass of the ball, 5.8 meters per second being the velocity as it leaves, which came from Tracker also, and 0.04 meters is the distance that the rubber bands were stretched. And that'll give you a spring constant of 210.25 Newton meters. So now if we go back over to Tracker here, we can watch through our flight sequence. As you can see, the ball is launching to right here, which is right just before it hits the floor. The next frame is right directly after the bounce. So this point right here is the point right before it hits the floor. So if we flip back over here, all of this data comes from Tracker, and it is that the velocity in the y initial direction is 2.08 meters per second. The velocity in the x initial direction is 5.41 meters per second. So, also coming from Tracker, your distance to the bounce is 2.63 meters. Your maximum height achieved was 0.47 meters, which is 0.07 meters higher than the launch point height of 0.40 meters. Now, if we continue on through the bounce, right here is, as I said, the frame directly after the bounce. So we can take and use our velocity graph to analyze the change in the velocity and find out how much energy is lost to the bounce. So if we scroll down here, we can find that the velocity before the bounce was 4.98 meters per second. The velocity after was 4.40 meters per second. So our kinetic energy before, still the same formula, 1/2 mv squared, is going to be that there was 0.124 joules before the collision with the floor. And then afterwards it was 0.0968 joules, which gives us that there was 0.0272 joules lost during the bounce. Now I'll hand it over to Mr. Big Cat to conclude this off for us.
Thank you, General Shathid. As shown in the slow motion video, we were successfully able to calculate the spring constant using Hooke's law for rubber bands on our catapult. That spring constant came out to be 210.25 newtons per meter. In addition to calculating the spring constant, we were able to analyze the velocity, maximum height, and the maximum distance traveled, which is 2.63 meters using tracker software. Had the tracker software not been available, you can also calculate the maximum distance traveled by multiplying the x component, which is a constant, by time. The energy lost during the bounce was calculated and found to be 0.272 joules. This energy loss was due to deformation in the ball as well as vibration. The Affordable Catapult Act is going to make not only catapults great again, but it's going to make America great again as well.
Good!
Yeah!